In the last video, as we were discussing chemical bonds, we talked about covalent bonds, which are bonds where electrons are shared. And we had said in the first video that bonds form in order for things to reach a lower energy state. And they do that generally, per the octet rule, by gaining, losing, or sharing electrons. So we talked about that sharing with covalent bonds, and now I want to talk about ionic bonds, where we have this give and take of electrons. So I'm going to write this down. Covalent bonds was 1, ionic bonds we'll call number 2. All right. What fundamentally holds an ionic compound together, or what do you associate with ionic compounds? Well, ions, which have what? They have charges, and those charges have repulsion among like charges and attraction among opposite charges. So what's holding an ionic compound together? The attraction between cations and anions. All right. So I'm going to write this, a little spoiler alert first. When you're thinking of ionic bonds, think of a give and a take of electrons. All right. It's not sharing, whereas covalent bonds were sharing, but it's a bond resulting from an attraction. And I kind of need to be careful with my terminology here. It is between, but it is really among cations and anions. All right. So as a quick refresher in terms of that vocabulary, right? Cations have a positive charge. And how do you get a positive charge? Something has to have lost electrons, right? Because when you remove a negative, you get a positive. And then anions are when you have a negative charge, and that's due to electrons being gained. All right, so keep that terminology in mind. If you ever get it confused, the way I always remember it is cation has a little plus sign right in the middle of it, that T. But there's all kinds of other amusing ways you can remember that type of stuff. Feel free to use whatever works, okay? So I'm looking around at my highlighter. Ionic bond, electrons are given and taken. So that's what I would imprint upon your brain. The first thing we had talked about with covalent bonds was the idea of the simplest unit, and that was a molecule, which was an independent entity. Well, that's kind of out the window now, because we don't have molecules. The ionic compounds have some repeating crystal lattice. All right, so let's get some terminology out there. Cations and anions, opposites attract. All right, so what is an ionic compound? It's a compound held together by ionic bonds. Compound held together by ionic bonds. All right. We don't have a molecule. We have what is called a crystal lattice. All right. So we don't talk about molecules, right? So there is no molecules, right? There's no independent species, no independent thing, right? What we actually have is a crystal lattice. All right? And you've probably heard of a lattice in terms of maybe like a lattice work as that crisscrossed wood underneath someone's porch, right? Or maybe in your garden you have a lattice for the bean plants to grow up, or maybe you've made an apple pie where you've got that interweaving pattern on the top. That's a lattice. So lattice is some repeating pattern, and for our purposes, we're talking about a crystal lattice as a repeating 3D arrangement of ions. All right, and I always end up drawing some version of this. I'll draw it out right now because it's important for our terminology, but it's not like mission critical that you do. All right, so a crystal lattice, you can have various types of arrangements, but the simplest one, coincidentally, is called simple cubic. All right, and it's like a simple cube, and you have your ions at the vertices. And if we look at something like sodium chloride, it happens to have that simple cubic structure. And we have maybe our chlorines here. I'll draw those in first. And we have our sodiums. And they are attracted, as I had said here, among each other. This sodium is not just attracted to one chlorine, right? That's not how Coulombic forces work. Electromagnetic forces are in all directions. So this sodium is attracted to this chlorine, and this chlorine, and this chlorine, and this chlorine, but it is repelled by this sodium, and this sodium, and this sodium. So there, like with water, we had said 2 H's and an O. That is something. Well, one Na and one Cl isn't something. It doesn't exist because it's a whole bunch of NAs and a whole bunch of Cls. In fact, and this starts to make my drawing look a little messy, this goes off indefinitely in 3 directions for as many cations and anions as you have. And that leads to it being brittle, and we'll talk about the brittleness of ionic compounds when we're getting into the general properties. All right. So I find that very interesting, the idea that when we talk about ionic compounds, we don't talk about molecules. All right. What we will talk about is a formula unit, right? Right. And all that is a ratio, right? So it just gives a ratio. Of cations to anions for some ionic compound. And I think that that's kind of a big eye-opener for chemistry students. Is like, there is no such thing as a salt molecule, right? Salt is just a bunch of NAs and a bunch of Cls, and it's a 1-to-1 ratio, all right? And we talk about that in terms of a simplest, right, formula. In fact, we had a name for that in our previous work, and we called that an empirical formula. And when we talked about empirical and molecular formulas, we had said that all ionic compounds use their empirical formula. And here's how we see that in action. Before we talk any more about a crystal lattice, I do want us to work in parallel to our covalent bond notes, where we had this idea of a simple unit and then qualitative and quantitative identification before we talk about this analogous term to bond energy. All right, so let's jump over to that. Qualitative identification. Again, I'm going to abbreviate identification, ID. Qualitative identification, when we had for covalent bonds a nonmetal and a nonmetal, for ionic compounds or ionic bonds, generally we have a metal and a nonmetal. I don't know if I said that wrong, but covalent, nonmetal, nonmetal, ionic metal and nonmetal. And I'm looking for my periodic table here. And we can determine metal as one of these things left of the jagged line, except for hydrogen, or nonmetal to the right of that jagged line. So that's a pretty quick and easy way to do it. In fact, if you look, for example, at something like NaCl, classic example of an ionic compound, sodium is right there. It is a metal. Chlorine is right there. It is a nonmetal. And sodium chloride is a classic example of an ionic compound. Other ones, I mean, there's plenty you could give, but you could have something like Al2O3, or maybe like MgF2, and so on. Those are all examples where you have a metal with a nonmetal, and in general, you'll put the metal first in the formula, the thing with the higher oxidation state, once we start talking about nomenclature, naming this stuff. So that's our qualitative identification. For quantitative identification, we're going to look at the electronegativity difference, and we already saw the answer. Okay. If our covalent bonds had an electronegativity difference that was less than 1.7, our ionic compounds are going to have greater than 1.7. We have some, and I'll abbreviate, electronegativity difference that is greater than or equal to 1.7, right? And what that really means is it is considered more than 50% ionic. We've reached a point where they are not sharing. There is a give and take It's not a tug of war. One atom is taking the electrons from the other thing. In fact, I always joke, it's like, say for sodium chloride, chlorine takes the electron from sodium, and then sodium just follows chlorine around, right? There's an attraction between them. Sodium just keeps following chlorine around. So electronegativity difference greater than or equal to 1.7. And just like a simple example, as we're looking at those, like for NaCl, sodium has an electronegativity of 0.9, and chlorine is a 3.0. So we've got 0.9, 3.0 for the electronegativities. The difference between them, 2.1. And I know some of you are like, oh, it's negative 2.1. Doesn't matter, it's the magnitude. It's just how far apart they are. Sodium has a 0.9 in this tug of war. Chlorine has a 3.0 in this tug of war. The disparity, the difference in their strength is 2.1, which is huge. It's greater than 1.7, which is an indication that it is ionic. And again, these rules aren't written in stone. It's like I said, it's not binary in terms of whether something is ionic or covalent. It's a spectrum, and we just happen to have drawn the line in the sand at around 1.7. So this subtraction thing isn't always perfect. In fact, most often the qualitative method of metal and nonmetal is a good way to go. All right, we want to get in lattice energy and our general properties of ionic compounds before moving on. So let us get, well, we've already used this. How about this? Already used it. All right, I'm giving up. Let's talk about lattice energy. All right. When we talked about bond energy for covalent bonds, we said it was energy required to break covalent bonds. Well, when we're talking about lattice energy, we're actually talking about the reverse scenario. It's an exothermic definition, and it's based on the amount of energy released when 1 mole of an ionic compound forms from gaseous ions. One mole of an ionic compound forms from gaseous ions. All right, so as we're looking at, again, this parallel between covalent bonds and ionic bonds, covalent bonds, we had energy required. Lattice energy, we're talking about energy released. Bond energy for covalent compounds, to break, and lattice energy, we're talking about forming. And for bond energy, we're talking about covalent bonds, and in lattice energy, we're talking about ionic bonds. So, good compare and contrast type of question for you teachers out there, spoiler alert. And I'm going to move this up just a little bit so that I can get in our general properties, and then we can be done with our ionic bonds. That may end up a little bit crooked, but we shall persevere. So let's talk about general properties. Again, these are not written in stone properties. This is just, like I said, in general. For ionic compounds, the first thing we had said for covalent compounds that they tended to have lower melting points, and that's due to the intermolecular forces holding those molecules close together. In ionic compounds, we don't have intermolecular forces holding molecules close to each other. We have Coulombic forces holding a whole lattice, a network of cations and anions together, so it's a lot harder to get things apart. So they tend to have higher melting points. And if you look at, we had said water melts around 0 degrees Celsius or whatever, and something like table salt, you're talking about, around 500 degrees Celsius, I think, or Fahrenheit. So much bigger difference because it's much harder to get these Coulombic attractions, those charges, overcome to get the particles apart. Now this one is kind of interesting in terms of conductors of electricity. So ionic compounds as solids don't conduct. So I'm going to put, they are poor conductors as solids. All right. And if we talked about what we were saying for our covalent bonds, we said that our covalent compounds can't carry a charge. Well, when you have a solid ionic compound, all those ions are locked in place. So it is another situation where it can't carry charge. Let me make sure that made it all on the screen. Yep. All right, it can't carry a charge. So if you were to hook up 2 electrodes to a chunk of salt, it wouldn't conduct electricity because all those ions are locked in place in there. So what does that mean, though? It means they're good conductors as liquids. And that's probably something you don't think about too often, right? And in a liquid situation, these particles are now moving around in a soup of those ions. And yes, you can melt table salt. You can get molten salt. And that would be a good conductor, although it would be fairly reactive for your purposes. But we have this situation where the ions can move. And also aqueous. All right, now I know I just sneaked that in, but there is a vocabulary term that we can mention, and we'll get a fair bit of use out of it later, but this idea of what it means to be aqueous. I think just looking at the word, you can say to yourself, it has aqua in there, so it's got to be something about with water, and that is exactly what we're talking about. Aqueous literally means in water. All right, and ionic compounds tend to be electrolytes, which means they separate into ions. All right, so these ionic compounds we can describe as electrolytes. All right, and that is a real vocabulary term. You've heard it in like Gatorade and stuff, humorously enough. Theirs is mainly a marketing idea, but ionic compounds are electrolytes in a solution. All right, and those electrolytes, these are things that dissociate to produce ions. All right, and what do those ions then do? They carry a charge. And what do we call carrying a charge? We call it conducting. All right. So electrolytes allow the solution to conduct electricity because they carry a charge, which I think is kind of an interesting idea. And I'll mention this now, and we'll have to address it in a later video, but when you put salt, a salt crystal, into water, you don't actually have any salt in that water because salt is a strong electrolyte. It dissociates completely, and you just have a bunch of sodium ions and chloride ions floating around in that solution. They're not locked into this ionic solid that we would call salt. And I'll say it again in slow-mo. In water, salt water doesn't have salt in it. It has a bunch of sodium ions and chloride ions floating around in it. And then kids always ask, like, oh, well, how do I know what salt tastes like? You don't. You know how sodium ions and chloride ions interact with your tongue. All right, very interesting bit of semantics, but I think it's kind of neat for us to just toss out there as an eye-opener. And then the last thing that we had mentioned was in terms of brittleness. They tend to be more brittle as solids. All right, and if you're wondering why, it's because there's a force balance taking place here. This sodium is attracting this chlorine, but it is repelling this sodium and attracting this chlorine. And so you get very specific distances between these particles, and they're locked in place. And if you put pressure on that ever so slightly, then that force balance falls apart and the whole thing just crumbles. All right, there are very specific distances we're dealing with here. And if you adjust that ever so slightly, if you put pressure on it, then it tends to just fall apart, right? And you've seen that with the salt crystal. If you just smack it, it'll turn into a fine powder. So for chemical bonds, we have covalent done, we have ionic done, and we can spend a little bit of time talking about metallic bonds in the next video.